It's the final topic of the CCNA series, and I'd like to say we saved the best for last because it's a cool one. TCP/IP version 6. This marks a pretty monumental day because TCP/IP version 6 has actually been out for a long time, more than a decade. I remember teaching back in 1990, 97, 98 timeframe. One of the first areas I taught in was Microsoft, and I was teaching Microsoft Internet Information Server 3. And I remember saying, I believe that the whole internet will be TCP/IP version 6 by the year 2003, because I pulled the date out of the air because I figured it's got to be by then, right? And well, 2003 came and went, and my prediction went unheard until now, until 2008 timeframe, and we're now looking at TCP/IP version 6 as a very viable alternative, and it's starting to move into all Cisco curriculums. So what we're going to talk about as we get into here is understanding the basic concepts in addressing. We're not going to be able to go in depth into everything TCP/IP version 6, but this will give you a very good idea of where this technology is going and what it's going to look like. First question I want to ask is, will we ever need to upgrade to IP version 6? Meaning we've survived this long on IP version 4. Is there really a need? We'll then look at the IP version 6 addressing format and what the new kinds of addressing look like. They're big. We'll then look at the headers and address types because there's many different kinds of IP addresses in IP version 6. And we'll do some in-depth exploration into what these new addresses look like and even basics of how we can start subnetting. Do we really need IP version 6? The answer is yes. But it's more of a hidden thing, kind of like spam. Email spam. Email spam in recent years has reached all new levels in that there are literally hundreds of thousands of spam emails being sent out every single minute all around the globe. We know there's a problem, but we've got spam filters that are good enough to detect most of the spam and filter it out of our corporate email accounts. So we just kind of are turning a blind eye. But we need to fix the spam problem. We need a solution. It's just as of right now, we kind of have this band-aid in place of filtering that people are just like, okay, we'll pretend the spam is not really there. In the same sense, we've got IP addresses on the internet, and we've had TCP/IP version 4 for years that has been running NAT. We have NAT happening to where we can have hundreds of clients share the same public IP address on the internet as they go out. So there's a problem. There's an IP address shortage, but it's so hidden. It's kind of like the spam filter. It's like, well, we'll just pretend that there's not really a shortage because NAT fixes most of that. The U.S. I have yes, Virginia. There is an IP address shortage. It's kind of like the famous Santa Claus editorial. But the USA, the United States, who invented the internet, is still sitting pretty in the sense that they have tons of public addresses left. A lot of them just sitting there idle and unused. It's the rest of the world where the problem is. Until very recently, how generous, right? The United States gave Asia and Africa a single Class C IP address range for their entire country. Wow. And it was expected that Asia and Africa would use NAT to have that one Class C IP address kind of last the country. Now, recently, they have gotten more and that the IP addresses are spreading out. But at the same time, there are extreme shortages in countries outside of the United States. So what I will say, I'll add this little bonus piece right here. The other countries are actually far ahead of the United States in implementing IP version 6 because they have a desperate need for it. The United States is kind of like, yeah, we know there's a problem, but it hasn't really affected us so much yet, so we're very slow in migrating. But the Department of Defense, the people who created the internet, have said the year 2008 will be a big year for them because that's when they'll move all their networks to TCP/IP version 6. So it's happening. The United States is just a little slow. So current IP addresses are poorly allocated. Agencies needing Class C back in the day got a whole Class B, and they now have all these addresses that they're just sitting on and not really using, especially college universities. College universities were the first adopters of the internet. They have tons of IP addresses that, well, I won't say all of them, but many of them have just I'll throw one of them out there. University of Utah. I was actually talking with somebody who worked on the IT staff there. They said they had 4 unused Class B public IP addresses, just because that's what they had. Nothing against the University of Utah. They just applied for that back in the day, and now they have them, and they're just not using them. So estimates on IP version 4 exhaustion is largely debated, meaning some people say by the year 2009 we'll be out. Frankly, I really doubt that, just because we've lasted this long, and I think we should be able to last a little longer. Some estimates go as far as the year 2041 where we'll be out, but hopefully by then we've migrated over anyhow. New network devices are on the rise. NAT is currently seen as a prohibitor of progress rather than a good solution anymore. That NAT is what allows our current internet version to survive, even though we'd have nowhere near the amount of IP addresses that we need. So I guess let me give you a picture of the future, in my humble opinion. I believe that in the future, when IP version 6 is everywhere, every single thing on the face of this planet will have an IP address. The technology to do that has been there for quite a while. We have cars that have IP addresses. We have refrigerators and microwave oven, Maytag makes them, that have IP addresses. So the technician can run diagnostics on the refrigerator remotely without having to send somebody out to figure out what's wrong with it. We have watches that have IP addresses, cell phone that have IP addresses. We have the technology to give pets, animals, dogs, cats, IP addresses. All of the pets that you buy at the pet store nowadays come chipped, is what they'll call it, which is a chip that allows you to scan the pet and see who that pet belongs to. Well, it's not too hard to modify that chip to have IP address to where you could go to dogquest.com and find out where your dog is, using some GPS signaling and stuff. There was a test done in New York City where people were volunteering to have chips the size of a grain of rice implanted in them that is biometrically powered, meaning their body energy powers these chips, and it allows them to be tracked wherever they go. It's part of an experimental program that is supposed to help with kidnappings, meaning children that are kidnapped will be able to be found much quicker because, well, you see where I'm going. If your children are chipped, they will be able to be tracked. Now that's somewhere in the middle of my digression there. We went from facts of cars and microwave ovens to my theories of pets and people. But my point in all of this is the technology is there. And when IP version 6 comes out, you'll have the infrastructure now able to support it. Likewise, in the future features, we're going to see IPsec everywhere, meaning IP version 6, this next version, has IPsec built in. So all network communication on every network can be encrypted. So you'll see a big security rise. You'll see mobility where we can actually move from network to network as we're moving. That will help with cars and things like that. It has better mobility functions, and IP version 6 has a simpler header than IP version 4, which will improve on the processing power of all the different routers that use it. So now let's talk about some of the addressing. IP version 6 addresses. When people first started hearing about it, a lot of people, including myself, thought it was going to be something like this. You had IP version 4, so it'd be something like that for version 6. They didn't do that. IP version 6 addresses look like that. They are 8 octets. I'll go right to left. 1, 2, 3, 4, 5, 6, 7, 8. With 4 characters each, it is now converted to hexadecimal, so A through F are valid characters, along with numbers 0 through 9. The point is that they don't want to do this upgrade ever again. We want to make sure that we can pick a protocol and stay with it forever. Now, I'm sure when people were creating TCP/IP version 4, they thought this will last forever, and we ran out of addresses. And here I am, IP version 6, saying this will last forever, and maybe some guy like me in 50 years will be saying, oh no, we thought we'd have enough addresses. But look at this. When we moved from 32-bit to 128-bit addressing, we moved up to that many addresses. I say that many because I don't know how to pronounce that number. Somewhere around here we have the millions, billions, trillions, and then you lose me. I think somebody told me once it was like a quintillion or a quintrillion. I don't know. It's a lot of addresses. Somebody far geekier than me figured out that with that many addresses, we can give every square inch of the planet Earth approximately 3.6 million addresses per square inch. Every 3 square feet of the Milky Way galaxy can be given an IP address with this scheme. So to tell you, that's a lot of addresses. We're not going to be running out anytime soon. So, because the addresses are so long, they decided to make them more manageable. They divided them into 8 groups. So instead of dots, like we have 192.168, we have colons. Each group is 4 hexadecimal characters each. Now you can see they're quite long to write, so they came up with rules to eliminate some zeros and make them easier to manage. First off, rule number 1 is in an IP version 6 address, you can eliminate groups of consecutive zeros by using a double colon, but you can only use it once per address. So you can see I had 3 groups of 0, and I was really able to shorten that by just representing those 3 groups by putting double colons. But you could only use that once in an address. You should never see an address that has 2 sets of double colons because otherwise you wouldn't know how many zeros went in each location. Rule number 2 to shorten addresses is that you can drop leading zeros. So things like 0050 become 50. 0AB4 becomes AB4. So that allows you to really shorten this down to make it more manageable. Now, it's still pretty long when you compare it to an IP version 4 address, but at least if you're writing it, you're not going to be writing addresses like that every single time. Along with the bigger address, IP version 6 also provides a simpler header. I mentioned this when I was talking about the rationale for moving. In icnd2, we talked about an IP version 4 header and all these different fields that are in there, like time to live, protocol, the checksum flag, all kinds of stuff in that header that makes the packet harder to process for every single router. Down here is an IP version 6 header. It still has some flags in there, like how many hops it can go. Oops. I missed it. This one right here takes the place of time to live, and the next header field provides a field for expanding headers and so on. And I don't mean to get into all those. The point is that it is much simpler. It's a bigger header, meaning lengthwise, it actually adds more data to the packet because our addresses are so big. But at the same time, it's simpler for a router to process because it doesn't have to look at as many fields. Now we'll get into the real meat of the differences between IP version 4 and version 6 as we look at how they communicate. First off, in IP version 6, there are only 3 types of messages: a unicast, a multicast, and an anycast. Notice that one is missing from the IP version 4 day. Which one? Broadcast. It's gone. Good riddance. Broadcasts are now a thing of yesteryear. In IP version 6, there is no such thing as a broadcast. It has been replaced by multicast, meaning one-to-many. By using multicast, I can dictate exactly where messages are sent to just a certain group of computer, all the computers. Now, I will tell you that using multicast, you can actually accomplish the same goals as broadcast, and there are some multicast messages that you'll see in IP version 6 that are very similar to a broadcast, but the good old broadcast is gone. We now have unicast, which is one-to-one, multicast one-to-many, or a group of people, and then an anycast, which is one to closest. Anycast is going to be pretty awesome because you can, with anycast, give multiple devices the same IP address. So let's say that we have 2 routers right here that connect to the internet. One of them is in a branch office and connects over here, and maybe one's a corporate office. Or hang on, hang on. I just went bad somewhere in that network diagram. We've got 2 routers, and we'll say they're both connected. They're redundant for each other in a corporate office. And we have a router here that connects to, one group of users, and another connection over here that's another group of users. With an anycast IP address, I could actually give both of these routers the same IP address. And when the users go out to surf the internet, they'll just use whatever IP address is closest to them. Now, this example that I gave is kind of silly. Um, Here's a better one. Let's say that you have the world. I know, an artist at his best. This is the world, and this over in North America, or here's Russia, this is Australia, you're catching the drift. So we've got the world, and let's take a worldwide internet site like eBay. eBay has servers all over the world. And today they actually use some pretty complex systems to make sure that they load balance correctly and are redundant. So they might have a bunch of servers in the United States, and when I go to ebay.com, it directs me to those servers and I access the ones closest to me. When I'm in Russia, if I go to ebay.com, there will be a DNS infrastructure set up that will somehow get me to the server closest to me. Now, to set something like that up, it's very complex, and you have to use load balancers, caching servers. There's a lot to it. But with an anycast address, you'll be able to, with IP version 6, just give all those servers the same IP address, no matter where they are in the world. And the routing protocols will automatically find the closest server to you anytime you're trying to communicate with an eBay website. Pretty powerful. So those are the types of messages. Now in red, you can see the types of addresses. This is going to be something we have to get used to as well. In IP version 6, your device can have many IP addresses, and oftentimes will have many IP addresses that it uses to communicate. There are 3 different addresses that are defined right now. First off is a link local address. This is something that you use to communicate in your layer 2 domain. For example, if you have people that are plugged into the same switch, they will use the link local address to communicate with each other. It's just one type of address that's used for local communication. The next step up is an interesting story. It's the unique or site local address.